Okay, take a moment and imagine this. You've committed to learning something big, something important.
Okay.
Maybe you're tackling like a complex new field for a professional certification, or perhaps you're preparing for a really high-stakes exam, getting into a top university kind of thing.
Right. A lot riding on it.
Exactly. And you've got this massive amount of information in front of you, a hefty textbook, piles of articles, notes, let's say easily 500 pages or more.
Wow, yeah.
And it's packed with intricate facts, maybe daunting formulas, historical dates, names you've never even heard of. Your goals seem straightforward, right?
Yeah, just learn it all.
You need to absorb as much of this information as possible, store it, and critically be able to recall it accurately when it matters most. Like during that exam.
That's the standard approach, isn't it? You just sort of treat the mind like a container, input information, stored away nice and neat, and then just pull it on demand. Like getting a file from your computer.
Yeah. It absolutely feels intuitive. We act like our brain is this super efficient recording device, just capturing every detail perfectly.
It's like a video camera.
But here's where the fascinating challenge comes in, and the core insight from our source today. What if your brain isn't actually built for that kind of perfect encyclopedic storage?
Okay, interesting.
What if its natural state, shaped over millions of years of evolution, is actually better at deciding what information is, well, unnecessary and just letting it go?
So, designed to forget.
What if its fundamental design is actually geared towards forgetting certain kinds of details rather than holding on to every single thing you encounter?
If that's true, then the usual strategies,
Yeah.
just rereading notes endlessly or trying to cram.
Yeah, brute force memorization.
That might actually be working against how the brain naturally operates. It's like trying to run complex video editing software on a computer designed just for word processing.
Right, you're not using the hardware the way it's meant to be used.
You're fighting the system.
And that's precisely the territory we're exploring today. We're diving deep into a really insightful book called Exam Brain Science, or in Japanese, AEA.
Okay.
Our guide is the author Yuji Ikegaya. And he's not just, popular science writer, he's a professor of brain science at the University of Tokyo.
That's a top-tier university.
Yeah.
Like comparing it to Tsinghua or Peking University,
Yeah.
right? Very prestigious.
Absolutely. And he has this deep background in neuroscience with extensive prior research specifically focused on the hippocampus.
Ah, the hippocampus. Crucial for memory.
Exactly. So his academic standing, his specific research focus, it makes his perspective on learning and memory incredibly authoritative. People really seek out his advice.
And it's worth mentioning the book itself points out this is a revised, expanded edition. He had an earlier bestseller aimed more at high school kids prepping for exams.
Right.
But he's updated it with all the latest brain science, broadened its scope. So while it might have started with high schoolers, the principles, they apply to anyone facing serious learning.
Professional certifications, uni courses, mastering a new skill.
Yeah, or even just wanting to learn more effectively in general. It really goes beyond just exams.
And the central argument, like you hinted at, is that our gut feeling about how to learn, it often doesn't match the science.
Our intuition isn't always right when it comes to the brain.
We have our plan for how learning should work, but as Ikegaya shows us, the brain has its own plan, one shaped by, hundreds of millions of years of evolution.
A much older plan.
So our mission in this deep dive is to unpack what he reveals about how we can actually remember more stuff, and just as importantly, remember it accurately, not just vaguely.
Yeah, precision matters too.
And he doesn't just give us tips, he gives the why. The brain science, the biological reasons, the evolutionary context for why some methods work and others, well, they might feel right, but are often a waste of time.
Or even work against you.
Consider this deep dive your shortcut, maybe, instead of years of trial and error with study techniques.
You can spend this time with us understanding the brain's rules of the game, the fundamental principles.
So you can work with your brain, not constantly fight against it.
Makes sense. Let's do it.
Okay, let's really unpack this. Let's start with that first big hurdle Ikegaya talks about, the challenge of simply remembering more information.
Right. The quantity problem.
And he kicks off with that initially surprising, almost frustrating idea. Your brain is naturally better at forgetting than remembering.
Especially the kind of stuff you need for exams.
Yeah, lists, facts, formulas.
It feels totally counter to what we're trying to do when we study, doesn't it? We're putting in all this effort to remember.
And the brain's default mode is like, nope, Don't need this.
Pretty much. From a biological view, its anti-instinctual setting is to discard info it doesn't immediately see as vital for, well, survival.
So what's going on in there? Structurally, how does this work? The author breaks down memory into stages, or types. First up, short-term memory.
Yeah, the brain's temporary holding area. Think of it like RAM on a computer, maybe. Very limited space.
How limited?
You can usually only juggle a few pieces of information there at once,
Hmm.
and it's super volatile. The data is only stored for a very short time.
Ikegaya uses that analogy, the boiling water one.
Oh, yeah, that's a good one. You put the kettle on for instant noodles, right?
Yeah,
Boiling water is in your short-term memory.
right there, top of mind.
But then your phone rings. It's a friend you haven't heard from in ages telling you some amazing story. You get totally sucked into the conversation.
Happens all the time.
How likely are you to completely forget about that kettle until you smell burning or hear it screaming?
Very likely. Guilty as charged.
Because the engaging phone call takes over. The boiling water info just sitting in short-term memory gets easily pushed out or just fades away. Something more interesting came along.
That totally resonates. And according to the author, all new information comes in through this short-term gateway first.
Yep. It has to pass through there. It's the first checkpoint before it even gets a chance to become long-term memory.
So where does that long-term memory actually live, if it makes it past the kettle stage?
That gets stored in the cerebral cortex, that big, wrinkly outer layer of the brain.
Ah, the hard drive.
Exactly. That's the main storage unit. That's where you want all that exam knowledge, the theorems, the dates, the vocabulary, to end up safe and sound, ready for recall.
But the big challenge then is getting the information from that small, leaky, short-term holding pen.
Onto that vast, more permanent long-term hard drive.
Yeah. And this transfer, it's not automatic, is it? There's like a bouncer at the door, a gatekeeper.
Precisely. A crucial structure decides what makes the cut. And that's the hippocampus.
The hippocampus. Ikegaya really focuses on this, doesn't he?
He does, because its role is absolutely critical in consolidating memories. He describes where it is deep inside the brain, kind of tucked away near your ears.
And it's small.
Surprisingly small for its importance.
Yeah.
Shaped a bit like a curved little finger, maybe a centimeter across, less than 5 centimeters long.
Wow.
But its job is huge. It acts as this vital relay station. It gets info from short-term memory and then makes a judgment call.
A judgment call.
Yeah, it decides. Is this piece of information important enough to send on for permanent storage in the cortex? Or should we just let it go?
Okay, so it's the judge. What criteria does this tiny judge use? Is it looking for complex math, historical significance?
Nope. Fascinatingly, its judgment is based on something way more fundamental, almost primitive.
Which is?
Shaped by millions of years of evolution, its main question is basically, is this information necessary for survival?
Survival, not, is this going to be on the test?
Definitely not. Think about what it evolved to care about. Is the formula for sulfuric acid as vital for staying alive as remembering those red berries made me sick?
Probably not, from the brain's perspective.
Or that rustling sound means danger? Compared to those, things like formulas, vocabulary, historical names, the hippocampus generally tags them as not critical for survival.
So there's this fundamental mismatch between what the hippocampus values and what exams demand.
Exactly. And here's another key point from Ikegaya. The cerebral cortex, that hard drive, it's not infinitely expandable like a computer's.
You can't just plug in more memory.
Right. There are physical limits. So the brain isn't just passively accepting everything, it's actively filtering. Forgetting isn't a bug, it's a feature.
A feature? How so?
It conserves that precious, limited, long-term storage space. It saves it for data that actually helped us survive and reproduce over our evolutionary history. Forgetting is about efficiency, survival efficiency.
This evolutionary angle seems really central.
It is. For hundreds of millions of years, the kind of learning animals needed was super practical. Where's the water? Which plants are poison? How do I avoid getting eaten?
Recognizing danger, finding food, finding mates.
Our brains, especially these deep, ancient parts like the hippocampus, were sculpted by those pressures. Formal exams, abstract concepts, lists of facts, these are incredibly recent demands.
You mentioned mammals are maybe 200 million years old. Human civilization, 10,000 years. Exams, maybe a couple of thousand.
Yeah, the timescales are wildly different. Exams are just a blink in evolutionary time. So it's no wonder our brains aren't naturally optimized for cramming abstract data.
It makes sense why it feels hard sometimes. The brain's
Yeah.
like, why are you showing me this chemistry formula? Show me where the food is.
Exactly. Its natural state isn't geared towards happily filing away abstract stuff because for most of its history, that info had zero survival value. Discarding it was the sensible thing to do.
Okay, so if the brain's default is to forget exam-style knowledge because the hippocampus doesn't see it as vital, how do we trick it? How do we persuade this ancient gatekeeper that, yes, this formula is important, at least for the next 3 months?
How do we get it into long-term memory?
Yeah.
Well, the author's answer here is maybe a bit underwhelming at first. The most effective way to make the hippocampus think something is necessary, even if it's just, say, the periodic table,
Yes.
is to send that same information to it repeatedly.
Repetition. Just repetition. The old boring advice.
Yep, repetition is fundamental. The source really emphasizes this. Sending the signal over and over creates an illusion of importance.
Like knocking on the door again and again.
Exactly. Eventually, the hippocampus goes, okay, this signal keeps showing up, must be important somehow, and it finally opens the gate, lets it through for long-term storage.
Which explains why practice makes perfect, or drill and kill, has always been part of learning.
Across cultures, across history, it taps into this basic brain mechanism.
But I can almost hear listeners groaning. Ugh, really? Just grind it out. It feels so tedious. Like there's no clever hack, just brute force repetition.
That's a totally fair reaction. And yes, the need for repetition is real. But here's where Ikegaya gives us the crucial nuance, the brain science part.
Okay, what's the nuance?
While repetition is necessary, we can make each repetition way more effective. We can reduce the total amount of grinding needed
No.
by increasing the impact or the intensity of the signal we send to the hippocampus each time we repeat. We're not getting rid of repetition, but we're making each rep count for a lot more.
Ah, so it's not about doing more reps necessarily, but making each rep more powerful.
Exactly. And the author introduces what he calls the 4 magic tools to boost this efficiency, to make each repetition stronger.
Magic tools. Okay, I'm listening. What's the first one?
The first tool uses specific brainwave patterns called theta waves.
Theta waves. I've heard of alpha for relaxation, beta for focus. What are theta waves?
Theta waves are interesting. They tend to show up when you're in certain states of mind, feeling curious, maybe a little tense or excited or anticipating something.
Okay.
And the key finding Ikegaya highlights is this. When theta waves are present, the hippocampus is much more easily stimulated. Memory consolidation becomes dramatically more efficient.
How much more efficient?
The book cites research suggesting it could reduce the number of repetitions needed by as much as 90%, maybe needing only 1/10 the effort.
Whoa, a tenfold boost just from brainwaves. That's huge.
It really is, and it provides a solid scientific reason for that old saying, interest is the best teacher.
Ah, okay. How does that connect?
If you're genuinely curious about something, if you find it exciting, engaging, you're naturally generating theta waves,
Right.
which makes your hippocampus way more receptive. You remember that stuff with far fewer repetitions compared to something you find incredibly boring.
That makes total sense. Think about hobbies. People remember insane details about their favorite sports team, or complex game rules, or movie trivia.
Effortlessly. Almost no conscious memorizing effort needed.
Oh.
But ask them to remember historical dates or science terms. It feels like climbing a mountain.
The difference is the interest generating those theta waves.
Exactly. The source had that great anecdote about the high school kid who got amazing at English vocab.
Oh yeah, not from flashcards.
No, from reading scripts of American TV shows he loved. He wasn't trying to memorize. His interest in the shows did the heavy lifting by generating theta waves. The learning was a side effect of his engagement.
His brain was working with him, not against him.
Precisely. Now, okay, fostering genuine interest isn't always easy, right?
Yeah.
Especially for boring required subjects.
Tell me about it.
But Ikegaya mentions another surprising trigger for theta waves.
Motion.
Motion, like
Yeah.
walking around.
Yes. The research suggests that the brain, just perceiving motion, whether you're physically walking, pacing, or even just riding in a car or on a train, can induce theta waves.
So that explains people who pace while studying.
It gives a scientific basis for it. That feeling of needing to move while memorizing might actually be your brain seeking those beneficial theta waves.
So does that mean listening to this deep dive or reviewing notes while taking a walk or on your commute could actually be more effective than sitting still at a desk?
Based on this science, it's a strong possibility. Your brain perceiving that motion might be boosting the hippocampus's receptivity, making the information stickier.
That's a super practical tip. Literally learn on the move.
It can make a real difference in efficiency.
Okay, so tool one, theta waves, sparked by interest or motion. What's the second magic tool?
Tool number 2 involves the amygdala.
The amygdala. I know that one involved in emotions, right? Exactly. It's another small structure about the size of an almond, right next to the hippocampus. It's often called the brain's emotion factory, handling fear, joy, anger, anxiety, sadness.
And how does emotion link to memory?
The link is incredibly strong. Research shows that when the amygdala is activated, when you're feeling a strong emotion, memory formation in the hippocampus gets a significant boost.
Like really significant.
Think about your own life. What are your most vivid memories? The ones that feel burned into your brain?
Almost always tied to strong feelings. Happy moments, sad times, maybe scary events.
Right. Those recollections have a powerful emotional tag attached, making them much stronger and longer lasting.
And there's an evolutionary reason for this too, I bet.
Absolutely. It's pure survival mechanism deep in our ancient wiring.
Oh.
An animal needed to remember, with crystal clarity, escaping that predator or finding that amazing food source or eating something that made it sick.
Emotion highlights the important stuff.
Emotion acts like a biological highlighter pen, marking critical survival events as maximum importance, do not forget. This system is still fully active in us.
Okay, but how do we use this emotional awakening for, like, learning the periodic table? It doesn't naturally make you feel intense joy or fear.
The author says we need to actively inject emotion. Don't just passively read facts.
Give me an example.
Take a historical event. Instead of just memorizing Napoleon exile to St. Helena, 1815, try to connect emotionally. Imagine being Napoleon.
Okay.
This guy conquered empires, held immense power. Now he's defeated, stuck on a tiny island in the middle of nowhere. Try to feel the despair, the frustration, the isolation he might have felt.
So engage the amygdala by empathizing or imagining the feeling.
Exactly. By connecting your emotions to the factual information, you create a much stronger memory trace. The amygdala flags it for the hippocampus.
That reminds me of that quote in the source about the battle description.
The yin-yang battle. Blood coated the sword hilts. Too slippery grip, yet they still shouted to kill the enemy.
Yeah. That's not just facts, it's visceral. It triggers an emotional response.
Precisely. It wasn't just relaying info. It conveyed the raw feeling of desperate struggle. That emotional connection makes the event incredibly memorable. It shows how coupling fact with feeling boosts recall.
Does it have to be negative or intense emotion? What about other feelings?
No, the source says any strong emotion works. Joy, surprise, curiosity, which links back to theta waves. Remember, anxiety.
So feeling anxious before an exam might actually boost memory temporarily.
It might. The book mentions that some people get that pre-exam memory surge, possibly because anxiety activates the amygdala. But obviously relying on panic isn't a great strategy.
Not sustainable, no.
So Ikegaya suggests more positive ways. Use humor. Make up funny mnemonics. Associate facts with silly stories or puns. Find something genuinely amusing in the material.
Laughter engages the amygdala too.
It seems so. Anything that creates a strong positive emotional tag helps.
So the dream scenario is combining tool 1 and tool 2. Make it interesting, theta and D. Tie it to an emotion, amygdala.
That's the powerhouse combo. Interest plus emotion gives the strongest signal to the hippocampus, making that info way more likely to stick with less repetition.
Okay, got it. Theta waves and amygdala. What's tool number 3?
Tool 3 is association. The basic idea is link the new stuff you want to learn to as many other things as possible. Things you already know, images, experiences.
Don't just store facts in isolation, build a network.
Exactly. Think of memory like a big web. An isolated fact is hard to find again, but if you connect it to lots of other points in the web.
There are more paths to get back to it.
Right. The source doesn't detail the exact neural mechanics, but the idea is that more connections mean more retrieval cues. If one path is weak, maybe another connection will lead you there.
Makes sense. What are some practical ways the book suggests for building associations?
Lots of ways. Learning vocabulary. Don't just stare at lists. Use the words in sentences. See them in context. Explore word roots. Associate them with images or actions.
What about concepts?
Think about how they apply in the real world. Connect historical events to current affairs. Create mnemonics, acronyms, rhymes, jingles that link new info to something familiar and catchy.
The book also highlights visual association, right?
Yes, very powerful. Our brains are great with images. The classic memory palace technique is all about this.
Method of Loci, yeah.
You create a mental map of a familiar place, your house, your commute, and you place vivid images representing the information you need to remember at specific spots along the route.
Then you mentally walk through the palace to recall them.
Exactly. Other visual methods include drawing mind maps to see the connections, or even just remembering where something is on a textbook page relative to a picture or diagram. Those visual anchors create associations.
The more vivid the image or connection, the better.
It seems to be the case. Stronger association, stronger memory.
Okay, so we have theta waves, interest motion, amygdala emotion, association, linking. What's the fourth and final tool?
The fourth tool is maybe the most crucial and perhaps the most counterintuitive: output.
Output, as opposed to input.
Exactly.
Sure.
Ikegaya stresses this based on brain science. The brain values outputting knowledge much more highly than just inputting it.
So retrieving information, using it, is more important for memory than just reading or listening.
Significantly more important. Actively recalling, applying, or explaining information sends a much stronger signal to the hippocampus than passively absorbing it.
How much stronger?
The book gives a striking comparison. Just inputting, like reading might take 4 or 5 repetitions to make something stick, but doing just one input session followed by one active output session can achieve a similar result.
Wow. One input plus one output is almost as good as 5 inputs. That's a huge efficiency gain.
It's massive. And it means that just rereading your notes over and over, it's one of the least effective study methods.
Even though it feels like studying.
It feels productive, but it's passive input. It doesn't give the hippocampus that strong, "this is important, I'm using it" signal that output provides.
So what kind of output should we be doing?
Shift your focus. Don't just reread a chapter. Close the book and write a summary from memory. Don't just look at solved math problems. Try to solve practice problems yourself without peeking at the answer first.
Actively retrieving.
Don't just review formulas. Try to derive them yourself or write them down from memory. Test yourself constantly.
And the source specifically mentioned explaining things to someone else.
Oh yeah, that's like the gold standard of output, often called the protege effect or Feynman technique.
Why is teaching so powerful?
Because when you explain something, you're doing multiple things at once. You're retrieving the info output. You have to organize it logically. You have to rephrase it simply, which forces deeper understanding.
And you're probably making associations as you explain it.
Exactly. You're connecting it to your listeners' questions or understanding. It's a potent mix of output and association. Sends a really strong signal to the hippocampus.
So find a study buddy, explain it to your cat, talk to the wall, just articulate it.
Pretty much. Active output is key.
Okay, this is incredibly useful. So to remember more, we don't just repeat endlessly. We make repetitions count using theta waves, interest motion, amygdala, emotion, association, linking, and prioritizing active output.
That covers the quantity challenge.
Yeah.
Getting more stuff in.
But, as the author points out, there's a second big challenge: remembering it accurately.
Right. The quality problem. It's one thing to remember something, another to remember it perfectly without mistakes or fuzziness.
And Ikegaya says this is hard because human memory is inherently fuzzy.
Yeah, fuzzy. By design.
What does fuzzy mean here, like out of focus?
Kinda. It means when we recall a memory, it's not always a perfect identical copy of the original input. There can be small changes, bits missing, distortions.
How could that happen?
He explains it by comparing brain circuits to computer circuits. A computer stores data as exact ones and nils. When you retrieve a file, it's a perfect copy.
Input equals output. Perfect fidelity.
Exactly. But in the brain, info travels as electrical signals along nerve fibers. To get from one neuron to the next, it has to cross a tiny gap, the synapse.
The synapse. Like a little transfer station.
Right, and at that gap, the electrical signal briefly becomes a chemical signal. Neurotransmitters are released, then back to electrical on the other side.
And that's where the fuzziness creeps in, at the synapse.
Yes, because the synapse isn't just a passive wire. It can adjust the signal strength. The output signal isn't always an exact replica of the input signal.
It can be slightly modified during transmission.
Exactly.
Yeah.
This capacity for adjustment, for slight variation across the synapse, is where the fuzziness, the inherent slight imperfection or variability in memory comes from.
He gave that example, right? Hearing ma dong mai, but remembering ma something may.
Yeah, the core is there, but the fine detail got a bit fuzzy.
Okay, but why? Why would evolution build a system that's imprecise? It feels like a disadvantage, especially for exams.
This is one of the coolest insights in the book. Ikegaya argues this fuzziness isn't a flaw, it's a massive advantage for dealing with the real world.
An advantage? How?
He uses that great analogy with the dog and the robot experiments.
Okay, walk me through those again.
All right. Task 1. Train a dog and a perfectly programmed robot to press a button when they see a circle on a screen.
Okay.
The robot. Give it one command. If circle, then press. Learns instantly. Perfect accuracy. The dog needs repetition. Show circle, encourage press, give treat. Maybe takes dozens, hundreds of tries. Its fuzzy memory needs that reinforcement and association. Circle plus button plus treat.
So round 1, the robot looks way better, faster, more accurate.
At that one specific task in a static setup, yes. But now, change it slightly. Show a triangle instead of a circle.
What happens?
The robot, programmed only for circle, sees the triangle and does nothing. Its perfect rigid logic has no instructions for triangle.
Okay. And the dog?
The dog, with its fuzzy memory, sees the triangle and likely presses the button anyway.
Why?
Because its fuzzy memory didn't necessarily lock onto perfect geometric circle. It generalized to something like, shape appeared on screen, pressing button gets food. It recognized the similarity, the general pattern.
Ah, the fuzziness allows generalization, seeing close enough.
Precisely. And Ikegaya pushes this with a thought experiment. Put the dog and robot in an ecosystem with 100 potential foods, but only teach them about 3.
Oh.
Both learn the 3, but eventually those run out. The robot, with its perfect memory, only recognizes those 3 things as food. It starves searching for them, ignoring the other 97 possibilities.
Because its memory is too precise, too rigid.
But the dog, its fuzzy memory of food is broader. It's not limited to just those 3 examples. It starts exploring, trying other things.
Trial and error.
Exactly. It might eat something bad, learn don't eat that again, memory adapting. Through exploration driven by its flexible, fuzzy memory, it finds other food sources. It adapts and survives. The robot perishes.
Wow. That really flips the script. In a changing world which nature is perfect, rigid memory is actually a disadvantage.
Because situations rarely repeat exactly. Rigid memory fails if the input isn't identical. Fuzzy memory allows generalization, flexibility, adaptation.
The dog's imperfection was its strength. It allowed it to adapt.
It didn't need perfect circle versus triangle distinction initially. It needed to generalize screen shape, press button. That was the relevant survival rule there.
It makes you rethink what we call flaws in memory. Getting things slightly wrong, maybe it's part of what makes us adaptable.
Exactly. Ikegaya quotes that Jewish saying, "Man's strength is precisely in having weaknesses. Our memory's fuzziness isn't a bug. It's a feature enabling flexibility, a core human trait computers lack."
That's a really profound shift in perspective. Okay, but we do need accuracy for exams. We can't just tell the examiner, well, it was sort of like that formula.
Absolutely not. While fuzziness is the default, we can train for accuracy. But like the dog showed, it's a gradual process.
How did the dog learn accuracy?
Remember, initially it couldn't tell circle from triangle, but we can teach it. How? Not by immediately trying to make it distinguish a circle from a very similar oval. That's too subtle at first.
So what's the method?
Gradual discrimination. Start with easy distinctions. Train it to tell circle from triangle, big difference, rewarding only the correct one. Once that's solid, move to something slightly harder, maybe circle versus square, then circle versus pentagon.
You progressively refine its ability to see differences, starting with the big one.
Exactly. Trying to get it to see circle versus oval right at the start would likely fail. The difference is too small for its fuzzy system to initially latch onto. Big differences first, then refine.
The brain needs to build pathways for broad distinctions before it can handle subtle ones.
That seems to be the principle.
Okay, how do we apply this gradual discrimination, this big picture first idea, to human learning when we need accuracy?
Ikegaya is really clear on this. When tackling a new, complex subject, do not start by diving into tiny details or trying to memorize subtle differences between very similar things.
Don't start with the oval versus circle distinction.
Right. That's inefficient, frustrating, and leads to shallow, easily confused knowledge.
So where do we start?
Start with the global view, the big picture. Get the lay of the land first. What are the main categories? The major divisions, the overall timeline, or core theories?
Understand the forest before looking at individual trees.
Exactly. Focus on the large differences, the clear boundaries between the main concepts or periods first. Establish the main framework.
Can you give an example from the book again?
Sure. Western art history. A beginner looks at Renaissance and Baroque and might just see old paintings.
Okay.
To learn accurately, you don't start by trying to distinguish 2 minor similar painters. You start by comparing periods with big, obvious differences, like Italian Renaissance versus Dutch Baroque.
What are the big differences there?
Subject matter, religious versus everyday scenes, use of light, soft versus dramatic contrast, composition, balanced versus dynamic, brushwork, smooth versus textured. You focus on these clear, defining characteristics first.
Establish those broad, distinct categories in your mind.
Precisely. Once you really grasp the major differences between Renaissance, Baroque, Neoclassicism, Romanticism styles that look fundamentally different, then you can start moving inward.
Comparing styles that are closer.
Yeah. You start noticing more subtle differences. You refine your ability to discriminate, just like the jog learning shapes. Eventually, after layering this understanding from broad overview down to specific movements, you can accurately distinguish nuances between artists within the same school.
But trying to see those fine details before you get the big picture is working against the brain's natural process.
Yes, the brain needs to move from fuzzy generalities to accurate specifics, building on the broad distinctions first.
And the same applies to history, like the Chinese history example.
Absolutely. The source strongly warns against starting history by just memorizing isolated dates and events like the year of the 1911 revolution without context.
Why is that bad?
Because it's rote learning. That isolated date is just a fragment to the brain. It has no connections, no framework, and information the brain sees as useless or unconnected.
It gets forgotten quickly.
Right. It's inefficient and doesn't lead to real understanding.
So the brain-friendly way to learn history is...
Start broad. Get the grand sweep. Understand the major dynasties, the big societal shifts like moving to semi-colonial, semi-feudal, the overarching period. See the whole timeline first.
Course first, then trees.
Only after you have that solid, big picture framework should you zoom in to the major periods within those larger eras. And only after that, layer by layer, do you drill down to specific years, key events, important figures.
So the super detailed stuff, the specific dates needing high accuracy, that comes last.
That's what the source stresses. Build the structure, then fill in the fine details.
This feels like it might take longer initially, getting the big picture first.
It might feel that way. But Ikegaya argues it's actually the more efficient, scientifically sound path to achieving accurate, deeply understood, and durable memory.
Because you're working with the brain's natural way of learning, moving from fuzzy to precise.
Exactly. It's not the long way around, it's the brain's way. Building the framework first gives the details context and connections, making them stick better and be recalled more accurately. You build a coherent mental model, not just a pile of facts.
Wow. That really changes how you might approach learning something new. Okay, so let's recap this deep dive. We've looked at two big things from exam brain science.
Right. Remembering more and remembering accurately.
To remember more, we learned the brain naturally forgets, especially exam stuff, because of the hippocampus's survival filter. But we can persuade it using repetition.
Made much more efficient by leveraging theta waves through interest or emotion, engaging the amygdala with emotion, building strong associations, and prioritizing active output over passive input.
And then for remembering accurately, we learned human memory is naturally fuzzy, which is actually an evolutionary advantage for flexibility.
But we can achieve accuracy by respecting this fuzziness and using a gradual, big-picture-first learning strategy. Start broad, then progressively refine the details.
And what really struck me and what you emphasized is that the book's biggest value isn't just the list of techniques.
Right. It's understanding the why, the biology, the evolution behind why these methods work.
It makes you see your brain differently, not as this perfect machine that's just being difficult when it forgets.
But as this ancient, incredibly complex organ with its own rules and history, rules shaped by totally different pressures than passing exams.
The book traces brain origins back hundreds of millions of years, right? And the hippocampus itself may be 200 million years old with mammals.
Yeah, that ancient architecture is still running the show from memory.
200 million years, compared to what, 10,000 years of civilization? A couple thousand years of formal exams?
The time mismatch is just mind-boggling. It's perfectly normal, completely understandable that our brains aren't optimized for cramming lists of state capitals.
They were optimized for surviving the savannah, not acing the SATs.
As Ikegaya puts it, you have your plan, pass the exam. The brain has its plan, survive and adapt.
And the key isn't to force our plan onto the brain's ancient plan.
No, it's to understand the brain's plan, its rules, its tendencies, and work with it.
Understand why it forgets, why output matters, why fuzziness helps, why it learns gradually.
And then apply these scientifically backed methods. Stop fighting your brain's nature and leverage it to learn more effectively.
It feels less like battling your memory and more like collaborating with it.
A much better way to think about it. It's not just about grades. It's appreciating the amazing system that lets us learn it all.
And thinking about this ancient brain in our modern world, it really makes you wonder, doesn't it?
It does. The implications go way beyond studying.
That seems like a really powerful thought to leave you, our listeners, with today.
Mhm.
How does really grasping this, that your brain has this incredibly ancient design, optimized over eons for survival and adaptation in a dynamic world, not for perfect data storage, how does that change the way you look at other parts of modern life?
Does it make you question other ways we try to squeeze our ancient brains into brand new roles or tasks? Things they weren't originally built for in our tech-driven world. Something to chew on.